So for me, it's a huge pleasure to welcome back Jonás. Jonás was a PhD student here at Física. He defended in 2017, so nine years ago already. A lot of things happened, pandemic, canos, whatever. After the PhD, he moved from Aragon to Argonne National Laboratory in Illinois. You see, some moment during 3 years. Welcome back to Spain, to the DPC, where he working with Silvia and also with Chad. And since 2022 is in IFAE. So working with Lyman-alpha forest, and it's the topic of today. So all yours.
Thanks a lot for the introduction. And just to mention that I was the first PhD thesis in cosmology here, in the center, so a long time ago. Okay, so I'm going to start with a general introduction to cosmology, and eventually I'm going to zoom in into the Lyman-alpha forest and exactly what I want to present, the result of a study using DESI data. So as we know, cosmology is really, in the end, a new science. It has like a little bit more than 100 years, because at the beginning of the 20th century, we thought that the universe was just a galaxy. And then, over time, now we have a coherent picture between the initial fluctuations, quantum fluctuation in the very early universe, and the entire evolution up to today for the large-scale distribution of galaxies. But there are still many open questions in cosmology, because we only understand like 5% of all the energy density of the universe, and then we have that most of the energy density goes into dark energy, that is something that is creating this accelerated expansion of the universe, and most of the effort today in cosmology is trying to understand this component. We have some evidence now, since the last year and the year before, that maybe it's evolving dark energy instead of the cosmological constant, that it was thought for many years, but we don't know that yet. Dark matter, we don't know the particle nature of dark matter, and it's something that we really want to understand. And it is also interesting that we can also answer other questions that we are not really used to from the point of view of cosmology. For example, to put constraints on the sum of neutrino masses, to know whether there are like relics or not. And this is traditionally more connected to particle physics, but it's something that we can also answer in cosmology. In order to answer those questions, we have different observables. The traditional one is the cosmic microwave background. For a very long time, it was the most constraining observable, because you have a lot of data there, it is easy to model, and you get information because you can see almost all the baryons there at that time, at these early times. But now, looking at the distribution of galaxies, also at the shape of the galaxies, because we have the shapes of the galaxies in the background, then the light goes through the distribution of matter and to us, and then this light gets curved because of all the matter that is intervening between the background and the foreground, and that is creating these beautiful arcs there, and we can extract a lot of information from gravitational data. And then the supernovae that were used from the very beginning to understand the accelerated expansion of the universe. And the crucial point here is that we need to combine the information from all these different observables if we want to answer these questions that I was talking about before, because you have different sensibilities to different phenomena, and the only way to really get accurate results is by combining them. And now we are entering in the stage 4 time of the different galaxy surveys. By this, what I am referring to is that in 2007, more or less, there was a convention in US, and they decided to classify future surveys as a function of the precision in the figure of merit of dark energy. And what they found is that the very early surveys were stage 1, and now we are getting to these stage 4 surveys that we have DESI, that is going to release the third batch of data very soon. Euclid, that is going to release the first one. LST is finishing now the commissioning, and Roman is going to be launched before the end of next year. That's what they promised. I'm going to talk about mostly the analysis of DESI data. DESI is a multi-object spectrograph in a 4-meter telescope. And the important thing about DESI is that it's able to take a lot of spectra in every pass. And in that way, you can take more spectra in 1 year than all the spectra that we're taking with SDSS, BOS, and EBOS over 20 years. And that's the amazing thing of DESI. Another thing is that it has been ahead of the schedule from the very beginning. So much ahead of the schedule that I was checking these numbers yesterday, that the nominal survey of 5 years is 98% complete. I'm not talking only about the bright time, that's already complete. This is the dark time, the difficult one. And now it has been extended because we have extra time. It's going to go at least for 1 more year. And the results that I'm going to talk about today is about the first data release that is corresponding to the first year of observations. The problem was that this analysis was quite complex. So we were still looking into the DR1 data. The DR2 data is out, but we decided to jump over DR2 and we are going to analyze directly DR3. And we are starting the analysis now and we are running the new simulations that we need and so on. But the idea is that what I'm going to present today is just DR1. So DESI, what do we do with DESI? We measure with very, very good precision the redshift of galaxies, quasars, and in the end we take these intermediate resolution spectra, not really high resolution, but it's enough resolution to also measure the Lyman-alpha forest. So the idea is that by taking this spectra, all these different galaxies, we have different populations that go from bright galaxies in the nearby universe, and we go to higher redshift. We have LRGs, ELGs, quasars, and very high redshift, about redshift 2. We measure the redshift of these, we measure these spectra of quasars that we can detect the Lyman-alpha forest. And these are the numbers that we have, and I was mentioning before, even compared to now, the 25 years of data, just 4 million spectra of SDSS at the very beginning. And with 1 year, it was like twice, so 3 times more. Okay, so now that we know why we can measure this Lyman-alpha forest, what is the Lyman-alpha forest? These are absorptions in the light of these background quasars by hydrogen in the intergalactic medium. So the idea is that as the light of the quasar is traveling through the universe and is getting resifted, you have absorptions every single time at the redshift of the Lyman-alpha line. And then you start to have all these different absorptions that look like a forest. I also wanted to mention, because it's going to be useful in the next slide, future slides, that we have 2 different types of contaminants. One is high column density systems. This happens when the light of the quasar is going very close to a galaxy. Here, in that case, you have a very broad absorption. And in the end, we can think about this like it is a different equation. In the same way that when we analyze ELGs and LRGs, we typically model them separately. This is the same. This is a different type of quasar because most of the absorption of the Lyman-alpha forest is in the intergalactic medium, so very low bias, and this is very close to galaxies, very high bias. It's a bias of 2, and the other ones are less than 1, over 1. So the idea is that these are completely different things, and we have to treat it differently. And the second thing is that we have contamination from metal lines, because the absorptions that we have are not only coming from the Lyman-alpha line, but also we can see here some metal lines, and some of them are so close to Lyman-alpha that they get confused. And you are going to analyze every single absorption as it is a Lyman-alpha absorption, but in reality, it could also be an absorption of a different line. And what you are going to have is that you are confusing 2 different lines that are coming from the same cloud of gas. So you are going to have an extra peak in the correlation function that if you do the Fourier transform and look at the power spectrum, it's going to be an oscillation. We are going to see this later. And now we're going to have a, let's see if it works. Okay. So what I was talking about, how as the spectra get received, because the light is traveling through the universe, you have the different absorptions that I was talking about before. This is just for Lyman-alpha and Lyman-beta. And you can see that in the end, you create this forest that I was talking about before. So now that we know what is the Lyman-alpha forest, let's go to cosmology. So what are the cosmological analysis that we do? The first one is the most traditional one, measuring the baryonic acoustic oscillations. So the idea is that we have the absorptions of the Lyman-alpha towards different quasars. So now, all these different absorptions, we compute the 3-point correlation function between all the different absorptions of different quasars, and also the cross correlation between the absorptions and the quasar positions. But I don't want to go into details, but the idea is that we can measure both, and in that way, on large scales, measure the baryonic acoustic oscillation. That this is this excess of probability of having a more matter or more galaxies at a particular distance due to in the early universe, you have these oscillations due to gravity and pressure, that you have overdensities, when you have the decoupling between the baryons and the photons in the plasma, in the regions that you have this overdensity, you were able to form more galaxies or more baryons, more gas. And this is exactly what we measure. As you can see, all these peaks are this excess in the probability, and we can use these measurements in order to constrain cosmology. So you can see there are a lot of peaks coming from the different samples, and this is the Lyman-alpha 1, that is the one at the higher redshift. And I wanted to mention that we were leading the DR1 analysis, and now we are also leading the DR3 analysis from IFAE. And that's the first type of analysis. Then the second one is full shape. Maybe you have heard about this for galaxies, but the idea is that instead of just extracting cosmology from the position of the BAO, you are going to now leverage the whole shape of the power spectrum. Because depending on if you change, for example, omega matter, or you change other parameters, you are going to change this shape. And it's a way that you can also put constraints on cosmology. I wanted to highlight here that this is quite important. One of the first that we measure is the Alcott-Paczynski effect. From the full shape, you get these constraints, and in black, you have the ones that you will get from just the BAO. So as you can see, we improve by a factor of 2 the constraint by using all the data from the full shape. And it is easier to see here in this diagram. This is H naught versus omega matter. This is important for this H naught tension. That is precisely the difference between the measurement from the late time universe, from supernovae, and the measurement from the CMB that are here. And now what we have is that all the different measurements from galaxies are there. And from the Lyman-alpha forest, when you combine BAOs and full shape, are in red. So the idea is that as you go to higher redshift, you have different degeneracies in this plane. And that's why it is very useful to have data from the Lyman-alpha forest, because you can break this degeneracy. As you can see, even though it's a single point at higher redshift, the constraints from galaxies are here in dust, and you go down to these other constraints by just combining with this single point of the Lyman-alpha forest. So the idea is that even though for a long time it was said like dark energy is just dominating at very low redshift, and the universe is almost Einstein-de at high redshift, and because of that you don't get a lot of information from the Lyman-alpha forest, but it is not really the case, because the Alcott-Paczynski effect is quite constraining for dark energy. And we can see this here, that these are the Alcott-Paczynski measurements from different galaxies, as you can see, the one is quite dark, and from the Lyman-alpha forest are small. And this is the results. Lambda CDN is the horizontal line, and for some evolving dark energy models are these other lines. You can see there is quite a difference even at high redshift. So if you were able to go to higher redshift, to intermediate redshift, it would still be quite constraining for dark energy. That's for Alcott-Paczynski, and the typical one that we always assume is when you just measure the 3-dimensional size of the BAO, that in fact it is important at low redshift. But with the Alcott-Paczynski, it's quite important to also have data high redshift. And that's why there are many new surveys that are targeting going to higher redshift, because you can put constraints on.
For the ones of us who don't remember, can you remind us what the Alcott-Paczynski effect
is? The Alcott-Paczynski is, if you assume a cosmology, when you are doing the measurements, in the end you have to go from angles and redshifts to co-moving positions. And if you are using the wrong cosmology, you are going to have a distortion. Instead of measuring circles, you are going to have something that is squashed. So you compare and this type of distortion is different from other distortions that you could have from resident phase distortions, for example. So it is possible to decouple both, and in that way, both constraints and cosmology. Thank you for the question. And yeah, for example, there is going to be a DESI tube that goes up to higher density precisely in order to measure this parameter. But that's not what I wanted to talk about. That's just to give a general picture of the Lyman-alpha forest. What I have been doing is to model the one-dimensional power spectrum. So now, instead of computing the three-dimensional correlation of different line of sight, I go to each individual line of sight, and I compute the correlation on this line of sight. And then I do a stack of everything. Why is that important? Because in that way, we can go to very small scales. Here the data, we do the measurements in kilometers per second. But the idea is that the smallest scale here is around k equal 4 inverse megaparsec. So these are really non-linear scales, very, very small. And the idea is that because we have so many quasars, we can go from redshift 2.2 to redshift 4.2. And at the higher redshift, as you can see, the statistical errors are large, but for all the other redshifts, the error bars are tiny. And that was one of the main problems that we had, that the error bars were so good that we have to fight a lot in order to get a good model. So in just the first year for observation, we had 600,000 high signal to noise forests, and that was 50% more than EVOS over 20 years. So we have much more data, and the models that we had two different groups analyzing this data. The group that was doing all the analysis in EVOS, they had the model. We were starting from scratch. And in the end, we were the only ones able to publish a paper with the cosmological analysis because everything that was assumed for EVOS was not working for this data set. We're going to see this now. Why do we care about this small scales? That's the main idea of this analysis, because in the end, you have three-dimensional correlations, you have VAOs, you can constrain dark energy, but why we want to do that? The idea is that with the Lyman-alpha forest, we can go to much smaller scales than from any other different group. And that's very important because there are multiple effects that only modify the matter power spectrum on small scales. For example, neutrinos. You have more neutrinos, you have a damping. Different types of dark energy, dark matter, the same. You have also a damping there on small scales. You have extra particles that could be able to explain dark matter, or just to have these particles in the universe. They would also change the linear power spectrum on small scales. And inflation. Different inflationary models predict different shapes of the primordial power spectrum. So if you have data from very large scales and very small scales, it is easy to prove deviation from a power law. So, having that in mind, the problem is that small scales difficult to model because this is no longer linear. We have to resort to high resolution hydrodynamical simulations. If you're familiar with these simulations, they require a lot of computing time. Running each of these simulations takes millions of CPU hours. So that's the main problem that goes into the nonlinear regime. And the second one is that we need hydro simulations because this Lyman-alpha forest observable depends on the ionization state of the intergalactic medium, the temperature, and the pressure. So you really need hydro. The good news is that you don't need all this subgrid physics that you need in order to model galaxies. Why? Because most of the signal, you can see here in the figure, is coming from smaller densities, between 0.1 and 10. This is the signal, and you want something that goes between 0.1 and 1. As you can see, it's there. And the overdensities for galaxies are more than 1,000. So this is really, really intergalactic medium, very far away from galaxies. And in that way, we don't need to dedicate a lot of computing time to this subgrid physics and to tune it and so on. And the other thing, this is a bit more technical, but that in the end, the ionization was in homogeneous and a very, very high redshift, higher redshift. This is quite important, but for us, a redshift below 4 is not important. We have run many simulations and found out that it was fine. So what we do in order to model This signal is that we run a suite of hydrodynamical simulations. We run 30 fixed ampere. If you are not familiar with these ones, it's just a trick in order to reduce the noise coming from the fact that we can only simulate small boxes. And in that way, we get all those different measurements for the parameters that we care about. There are two parameters related to the cosmology. I'm going to talk about this more in detail later, that are the amplitude and the slope of the linear power spectrum on the scales that we care about. It's a smaller scale that we prove, and at a particular phase. And then some parameters related to the state of the intergalactic medium, that is the mean flux, so related to the ionization, the two parameters related to the temperature, and one parameter to the pressure. That way, we get all this data and we use it to train an emulator. And an emulator is just a very fast machine learning model that is able to interpolate between the different measurements from this simulation so we can do inference. Just think about this like a fancy interpolator. Now that we have this here, that is the signal from the emulator, and this is containing everything related to the Lyman-alpha forest. But as I was mentioning before, we have contaminants. If we wanted to model also these contaminants in these simulations, this simulation will need to have also subgrid physics. It is impossible to have a suite of simulations going through. With this resolution that we require, that is 30 kiloparsec, that is super high resolution, also have the different contaminants. It is impossible, so what we do is to marginalize over them. So it is that we have the signal just of the Lyman-alpha forest there, and we have to model all these other terms related to metals and high column density systems. We have to dedicate most of the time in this project in order to understand this. Because before us, in EVOS analysis, the only thing that was modeled was this oscillation here of Lyman-alpha with silicon 3 because of this confusion that you will have a peak in the correlation function, you have these oscillations in the power spectrum, and it was to assume to not depend on K. As you can see, it's clearly K dependent. So my point is that the error bars were way larger, and just by using this was enough. Now, you can see here the chi-square that we get if we switch off this term, but also if we switch off other terms of other lines correlating with the Lyman-alpha forest, other types of contamination. So if we don't model all of this, the fit is that is what happened in the very beginning. We have a probability of 10 to the minus 96, I think, that our model was correct, the one that was used for EVOS. So yes, we have to dedicate a lot of time to understand this. And there was a very simple model for ACD contamination that it wasn't good enough for this data. So finally, we have this beautiful model. We have three parameters in total, because we have to model the redshift dependent on many of these terms of the contaminants. There are only two cosmological parameters I will talk about next. 16 for the state of the intergalactic medium, the redshift evolution, the mean flux, and all these parameters I was talking about. 16 for metals, for all those different correlations, 8 for ACDs, and 11 for systematics, because traditionally what it was done is to assume you have errors in the resolution of the spectrograph because you can characterize this with a particular precision. But that wasn't good enough for us because we want to extract all the information that we can from smaller scales. And these errors go into the smaller scales. So assuming a fixed value in the covariance matrix, that was not good enough. What we are doing is marginalize over this signal because the idea is that it can be described with very good precision with an Gaussian. So it was easier to marginalize over these systematics that include them in the covariance matrix. Finally, we have this model that what ends over here is the data points from the measurements and the shaded areas and the best fitting model. So I'm getting different points from the NCFC chain, evaluating the model and taking the average and the standard deviation. As you can see, we are describing the data quite well. And there are some places that you see a small offset. This is because the covariance matrix is highly off-diagonal because of some of the systematics, some of the way that we do the measurements, and also the errors on the emulator. So it looks that for some cases it's not quite good, but the probability of the fit is 22%. So we were quite happy with the results. And now, finally, going into cosmology. This is one of the most difficult parts I want to explain is why we measure this amplitude and slope of the power spectrum at small scale. So it is that because these measurements are on a very small scale that I was showing you. In principle, we could say, okay, we want to constrain the typical AES and NS parameters, but these are defined especially for the CMB, a super large scale, 0.05 inverse megaparsec. So for us, it makes more sense to go to a smaller scale, the scales that we use. Okay, and we go to this scale that is approximately 1/1 inverse megaparsec. Then redshift 3, because it's the middle redshift of all the redshift that we measured, the 2.2 and 4.2. And in this way, we define the different parameters that are related to the linear power spectrum and at those scales. And we measure just the amplitude and the slope with a normal field. Okay, we can constrain the information into these two parameters because the universe is almost isolated de Sitter at redshift greater than 2. So it is that omega matter is greater than 0.9. It's a good approximation. Really, that's general for all the models that are more or less compatible with the CMB. With the best fitting model, the CMB is 0.95, I think. So it's almost as the In that way, the growth of the perturbations in the universe is cosmologically independent for this type of universe. The growth of density perturbations will be this, and for the velocity perturbations equal to 1. If you remember, the velocity perturbations go with omega matter to this gamma parameter that has to do with the law of gravity. If omega matter is close to 1, growth is almost equal to 1. So we don't have to care about this growth of this cosmology dependent on the growth of densities and velocities. The nonlinear growth is also cosmology independent. So you can show for the extended Sitter universe that not only the growth on the linear scale, but this nonlinear growth that you have due to gravity it is also characterized by some fixed parameters that don't depend on cosmology. And finally, because the data is in kilometers per second, and we set the constraints on kilometers per second, we don't depend on the value h naught. So in the end, the idea is that all the cosmological information of the P1D can be compressed into these parameters related to the primordial power spectrum, to the amplitude and the slope. And in that way, our constraints are model independent in the sense that independently of the value of omega matter that you assume, omega matter is not going to change anything. So your constraints will be the same. This is similar to what we do with the BEOs. With the BEOs, we provide the alpha. We don't provide the omega matter that you would get. It's interesting because now, if you want to use this cosmological constraints, in order to constrain new models with, for example, massive neutrinos, or you want to constrain running of the spectral index, you can do it because this is cosmology independent. It's the same as for the BEOs. And in order to show you that it works, these are the linear power spectrum at redshift 3 from the analysis of Planck, when you have a free value of massive neutrinos and here of curvature. And this is what you get after you do a compression, that in the end what we are doing is to fix the amplitude and the slope of the power spectrum at small scales. And by fixing this, you can see that these large variance that you have in the initial power spectrum now is super small over this range. That's the range that we care about. It's smaller than 1%. That is the area. So the point is that even in a realistic case, without doing this approximation like 10 de Sitter, this is true, and this is for redshift 2.2, that is with the worst case scenario. As you go to higher redshift, you are closer to omega matter equal to 1, and the compression is even better and it's below 0.1%. So, okay, so these are the parameters that we want to measure and we care about, but because the modeling relies on this emulator that was trained with a suite of simulations, it could be that it can extrapolate very well to a different suite of simulation or to the real universe. So you have to show that the model is robust. So we decided to analyze other simulations with higher resolution than ours and bigger ones, just to see whether the constraints were compatible or not with the truth in that simulation. And that's the left figure, that all the different posteriors are compatible with the cross, that it will be the truth. So we are compatible with the truth at the 1 sigma level, even though that these simulations will run with different codes, different resolution sizes. And then we did a lot of blinded data analysis tests. For example, here I'm showing the CS1 to understand that this is analyzing just the data at low redshift or at high redshift, and all the data, and as you can see, the results are perfectly compatible. And we did more than 26 different analyses of variations, and all of them were compatible. The ones invaluable. So once we were happy with the results, we decided to apply. And what we got is this posterior here in blue, and you can compare it with the posterior from the CMB in black under the lambda CDM model. This is going to be important because what we want to constrain are these extensions. And you also can see different other posteriors with different colors that are coming from previous analysis. And the first thing that you're going to notice is that, wait, you are using more data, and now your constraints are worse. What is happening there? So the idea is that in previous studies, they were making a lot of assumptions. Like they could use models for metals and ACDs that were not very complex. They were not incorporating the errors in the emulators, even though their simulation were way worse than ours. And the treatment of systematics was a bit worse. So it is that they had super precise results, but very, very far away from Planck, for example. Even going for some crazy models of, for example, of running of the spectral index that could try to have consistency with Planck, but not even with these models, you always had this 3 sigma inconsistency of 5 sigma, and there were not known models of inflation that could solve this concept. So there was something fishy with the results. For example, these are 2 different analyses of EVOS data using 2 different emulators, and as you can see, depending on the emulator, they are jumping from one side to the other. And this second analysis, they are also using extra priors on cosmological parameters and parameters of the intergalactic medium that were helping them to tighten the constraints, but they were also using very simple models for the contaminants. So we didn't try to have the most precise results. We wanted to have the most accurate ones. This is in the end DR1, and we can fight to have better constraints in the future. So in the end, we were quite happy after doing the unblinding that we were on top of Planck. Now let's go to the interesting part. So I was showing the constraint from Planck lambda CDM before, and now we can see the same here in orange. But what is interesting is what is happening when you start to open the parameter space for some of these extensions. For example, we know that we have massive redshift, and this is what happens. That is a bit bigger. If you have free number of light species in the universe, you go to the big one. And when you open the space for running and running of the running, we'll talk about this later. That is depending on these inflation models, you get posteriors that are super large. And that's for these cases where our data is very constrained. You can see here our measurements are model independent, and when combining with Planck for these different extensions, we're going to help in the constraints. In order to see this more visually, it's not so easy to explain this plot, but the idea is that I show in every panel is the measurements of the linear power spectrum at redshift field from Planck and taking different points from the chain and divided by the phase fitting results. So in the end here, for very fitting results for lambda CDM. So this is just showing the error bars from the Planck data, and this is our measurement that we measure a point with an amplitude, that this is the error in the amplitude, and a slope, and this is the error in the slope. Our best constraint is in the slope, so that's why it looks quite compatible with everything, looking at the amplitude. But if you look at the slope, this is the range of the slope that are allowed. And for this running and running of the running, as you can see, the slopes are getting crazy. So it is not so easy to see why our data is so constraining, but that's the idea. And now what happens when you start to open the parameter space is that the constraints from Planck in the linear power spectrum are very similar over the range of scale proved by Planck. You can see more cases, but as you go to smaller scales, the constraints from the CMB are no longer so good. And that's why our measurements are very good, because these are the scales that we measure. Planck doesn't measure these scales, so the combination is very useful to tighten the limits of these different effects. So now let's go to the results. So this is for inflation. So the idea is that in the very early universe, we have this inflationary phase that the universe grew very, very quickly. And the idea is that in the plain Landau model, what we assume is that the primordial power spectrum is adiabatic, scalar, and a power law. But even the most simple inflationary model, a slow roll and so on, they predict that you have also a running of the spectral index. This is just a Taylor expansion of this primordial power spectrum, and you have an amplitude, let's see, the slow, that's called a spectral index, and then the running and the running of the running. That is how it changes with Taylor. And all these quantities can be related to the shape of the primordial of the potential of the inflation. You can see this exponent goes there, and this n star is the number of e-foldings, so how much the universe grew over that time. And so putting constraints on these different parameters, like the running of the spectral index, can help to constrain the potential of inflation. And you can see there for different inflation models that you have different predictions from the value of the running and also the spectral index. As I was mentioning in the beginning, because we have this data so far apart, it is easy to get deviation from a power law. So now let's go to the results. So what I'm showing is the constraints on the parameters that we really measure, so this amplitude and slope on small scales, and now also on the running of the spectral index and the running of the running. In blue, you have the result from Planck, and in orange, from the combination of Planck and our measurement. As you can see, the posteriors are getting much, much smaller. We are improving the results by a factor of 2, more or less, and we are compatible with a perfect power law. Less. And the idea is that you could say, okay, but this is Planck, very, very large scale, but we have also CMB data that goes to smaller scales and LSS data that is in even a smaller scale. So what happens when you combine with everything? So now the results from the in green have a combination of Planck, ACK, and SPT from the latest data release, state-of-the-art of CMB combination, or with temperature, polarization, and lensing, so everything there. And density are 2BL. And after including our measurements, we go from green to red. So the point is that we are still improving a lot. And this is just the consequence that the Lyman-alpha forest is proving the smallest scales. So that's why we still improve a lot of the results at factor 1.3 and 1.9 for the running and running of the running. In terms of the whole expansion of the primordial power spectrum, we are also improving the constraints on NS by 10% more or less. And this is interesting because, as I was mentioning, it is directly connected with the number of e-foldings. So right now, the best constraint on number of e-foldings are coming from this combination. Going to other of the things that we can constrain is the relics. So it means that in the very early universe, as we know, the neutrinos were in equilibrium with the primordial plasma, high temperature, as the temperature was going down, they decoupled. And after the electron-positron annihilation, you get to this relation between the energy density of the neutrinos and the photon. And the important point here is that you have these n neutrinos that in the standard model of particle physics, it has more or less that. It's not exactly 3, it should be 3 if the number of neutrinos 3, right? But it's a bit different because they were not completely decoupled. I read some papers, but in order to explain this, it's beyond what I can explain. But the idea, what is really interesting is that if you had other light relics in the very early universe, you will have a change in this number. You have an N effective, is L delta. So for any value that you get extra or N effective, it will mean that you have an extra light rally in the early universe that maybe you're not able to measure now because the interactions are even weaker than with neutrinos or whatever. Okay. And we can measure this because this different excess in the number, because of this extra variability particles, you will check the linear power spectrum on small scales. You can see that. So directly now to the results that we get from the combination of all the data, we go from green to red. And this is an improvement of a factor 1 point, like a 20% more or less. And we are perfectly compatible with the standard model prediction that are this DESI line, speaking there. Note that in previous studies, for example, Planck was a little bit off, and people started to wonder why it was smaller than the but in the end was more or less one sigma. But anyway, so we are improving this. It is interesting that these are the upper limits that they say current. This is after Planck, what you were getting for the NFFT, the error. This is Simon's observatory that is running now, and it was CMBS4 that at the end I think is not going to happen. But the idea is that by combining our measurements with the ones from Planck, we are going here. So better than the CMB with the ANISO observatory. So we are really improving, even though it's just a factor 1.2, this is quite important compared to what you will get with new servers. Finally, about massive neutrinos. So the idea is that because if you have massive neutrinos, you have so much clustering on small scales because these are relativistic. So if you had dark matter, it would cluster much more than what neutrinos would cluster on small scales. And this is creating a damping on the power spectrum on small scales. Just take a look at the DESI lines. The other lines are what happens when you fix different things in the early universe. But the idea is that that's the damping that we expect. And because we can put constraints on this amplitude of small scale, we can constrain on the small neutrinos. From the oscillatory experiments, we know that the neutrinos are massive, and we can put lower limits on their mass that are 59 electron volts or 100 electron volts, depending on the hierarchy. This is whether you have two massive neutrinos or two low mass and one more mass, so one low mass and two more mass and so on. But in the end, the idea is that you have these lower bounds there that are these DESI lines here. And the combination of all the external data is in green, and what we get in red, you can see we are not improving almost anything. I think it's 2%, nothing. But the idea is that this combination of external data sets is already in tension with the constraints that we get from oscillatory experiments, which is weird because we will expect to have larger values. But the point is that these constraints that you get from this analysis of CMB data with an scale structure are model dependent. And when you open the parameter space, for example, for evolving dark energy, the constraints get relaxed and peak more or less over here. And in that case, our constraints are again important because we can tighten the constraint, for example, compare Planck with a combination of Planck and our measurements. We are improving quite a lot there. So it's still to be seen what happens when we have better constraint for evolving dark energy because it's not clear what is happening for neutrinos. And the other thing is that because of this idea of different combinations, some data sets can be subject to different systematics, we wanted to check whether we were able to get a measurement just from large scale structure on the sum of neutrino masses. This is a combination of BEO, full shape, our measurement, and also baryonic synthesis because we need this BBM measurement in order to measure the amount of baryons, omega baryon. That's the only external data set that you need besides direct scale structure. But you can, in that way, put constraints on the sum of neutrino masses that is here in orange, independent of the CMB. But this is interesting because of these different combinations. In the end, we have the CMB data, we should use it, but in all these papers that the people do at DESI, they are super happy of show this result for the different combinations. And it was nice that it's the first time that can be done by adding the Lyman-alpha data. So just to recap, the Lyman-alpha forest is a very useful proof of the large scale structure and cosmology at the high redshift. We carry out this cosmological analysis of the DESI DR1 data. We have to run hydrodynamical simulations or analyze over different contaminants. But the idea is that after we were really sure that the analysis was robust, we unblind and we got these constraints compatible with Planck and the lambda CDM and tightening the constraints on the sake of the primordial power spectrum, like relics and massive neutrinos when combining with other datasets. That's it. So if you have any questions,
Go first.
very nice talk. So can you go back like 3 or 4 slides to the one, this one?
Mhm.
So if I understood this correctly, in order to reconcile oscillation mass for the neutrinos, oscillation measurements for the mass of the neutrino with your results, you actually need a time variation in the dark energy.
Exactly. So this is for lambda CDM. And you can see the posterior. This is the bound, the lowest bound that you get from oscillatory experiments for normal ordering. And this is inverse ordering. So it will be already ruled out, the first one, and the second one is under choosing ruled out. So you're starting to give tension. And when you open the space for evolving dark energy, you move the peak. And instead of being at 0, it is peaking at a positive value.
And the optimal value for the omega of this evolving dark energy does more or less agree with the other experiments.
Well, this is what you get when, I'm not redoing the analysis here with the evolving dark energy, but I'm looking at the papers, the DESI paper that they published with the DR2 data, and the combination then DES also published, also combining and so on, and all of them are the same. That if you have this evolving dark energy, you are moving the peak of the small neutrino masses. It's a general prediction. In the end, but if I were to include that and to tighten, I will see whether I tighten the results or not a little bit. But the idea is that this is a general prediction that you get not only here, but sorry. You have, what I can mention is that I know that there is an MOU with WIF. I think that's still happening, right? So the idea is that in the very beginning, WIF wanted to take a lot of time to do BAOs. But now, because you have so many quasars in DESI, the idea is that because they have higher resolution, they can measure the P1D even better than in DESI, in smaller scales. So this is going to be the measurement of the P1D, one of the main targets of the WIF QSO.
So for the next talk, to see a lot of cosmology from time to time is great. So at the end, then, well, you can put some constraints more in the inflationary models because you are talking about the power spectrum. So basically, you are in this. So at the end, you are getting that with you have no runnings. With a power law is good enough.
With the precision that we get here is a power law is good enough. Different inflation models are predicting runnings, but typically they predict a running within this range.
Okay.
And we are sampling now.
So you cannot rule out any.
We can rule out some. I was looking into this. I'm not really an expert on that, but some multi-field inflation models that they were already ruled out. But I know about some of the things I read in the papers. I'm not really an expert. I started to work with some people that are expert on this and IFAE. I can tell you more in the future. But these are, for example, the Phoenix survey. I don't know if you are aware of this one. They want to measure the running, and then also non-Gaussianics. But measuring the running is like one of the most important things that they want to measure. And the precision is not so much better than the one that we are already getting here. So I mean, it's an important target for all these.
I guess that they want to measure with another proof.
Yeah, the idea of Phoenix is that you have lower redshift precision and lower spatial resolution, but it's full scale. So they want to be cosmic variant dominated up to redshift, I don't remember, redshift 3 or something like that. Yeah, I was really involved in Phoenix a long time ago. But yeah, that was one of the targets.
Probably the blending of the sources is going to be funny.
Yeah, that's the thing. And the limiting magnitude is not so deep. So in the end, it's full sky, low spatial resolution blending, but they only care about the brightest thing.
Yeah.
So in principle, you can do some of the blending. I haven't concluded that. I was producing some of the mocks, and it was like,
Yes. And also, I mean, this is producing these the latest, the tier 2 solutions, this evolving dark energy. How well the systematics related with the selection are affecting the different groups? I don't know if, because you have so many, let's say, the density of your tracer is so high that perhaps you don't care very much about the systematics, which is the more safe sample for the systematics.
so I think LRGs, in general, like classically everywhere, like because they are bright, you can really see them. But you don't have so many nearby that you have so much problems with fiber collisions that you still have for ELGs. I don't know, it's difficult. For example, for the Lyman-alpha forest, in Bosch, it was one of the samples that almost nobody believed. And now it's like one of the most secure samples because we can finish the results earlier because it's much more linear to the point that you can use linear theory down to 40 megaparsec. So it's like for galaxies we can do. But the problem is that for Lyman-alpha, you have to, well, care about problems like the distortion matrix that it is because of the fact that you, in order to measure the continuum of the quasar, you have to assume that it's like a sort of power law, and in reality it's not a power law, and you have to marginalize over this power law. I mean, you have systematics everywhere, but the idea is that even though you have errors, and different type of errors for different observables, this is just quasars. These are emission-like galaxies, emission-like galaxies, LRGs, bright galaxies, but they are all moving, as you can see, but the best fitting model is going more or less in the middle. I don't know. I am more concerned about supernovae at very low redshift, below redshift 0.1, because that's the most important sample. The idea is that if you look at evolving dark energy, the precision of the constraints are like 3 sigma that you detected, just with the combination of CMB and DESI data. And that scale structure also you include DS. But if you include these supernovae at very, very low redshift, then you go to almost 5 sigma. So this point there, this a single point, is super important. And over a range of physics that you have supernovae and large-scale structure data, everything is on top of each other. So this extra sigma coming from just that. And most of these supernovae are very old because this is like local universe, which you have to wait for a new supernovae, not like you can go for larger area. So yeah, that's like the weakest point in my opinion of all this analysis. But well, 3 sigma already with CMB and large scale factor, so it looks like there is something there.
For the Hubble constant, this go in the right direction to solve it, or
it helps a little bit, but not so much. Well, I was showing this before. This is CMB, and this is low redshift supernovae. So as you can see, there is a huge gap, and now large scale structure is more or less in the middle. So maybe, I don't know. It's not clear because even with evolving dark energy, you solve a little bit the tension, but just a little bit. I don't remember whether it was like alpha sigma or 1 sigma, but maybe you move everything a little bit and then there is not, I don't know. Thank you.
Since you were mentioning the different data releases, and you were also commenting on the number of objects in Sphere X, since you may have heard about the data releases that we do here. So what is the difference between data release 1, 2, 3 of DESI? Because
yeah,
that is something where
year 1 is including the first year of the survey and also the survey validation. And it's important survey validation because in some regions you have more signal to noise than in all others over the entire survey. Then year 2 is including the first 3 years of data.
So every year it covers the whole sky or chunks?
Chunks, yes.
Okay.
The idea, well, depending on the object, you observe it once, twice, or 4 times. For example, for the quasar of the Lyman-alpha forest is 4 times.
Okay.
So, and well, even more now that we have extra time. But anyway, the idea is that for DR2, 3 years of data, and for DR3, that is the one that we are going to publish next year, if the nominal survey, the 5 years of nominal survey. And then there is going to be also a DR4 at some point, including all the extra data. But for most of the science cases, DR3 is going to be like the most important one.
The one.
When is the DR2 spectra being released?
It should be released, I don't remember exactly, but soon, because I think it's October of this year. I'm not completely sure, but I think it's that because now everybody is switching to work on DR3 data, and the idea is that because no one is going to work on that, it's to the public.
So we're going to have JPass and
Everything.
Gaia at the same time. So it's like
As usual.
Well, I did this analysis for DR1 data. It was already public when I was finishing the analysis. And I knew of a external group also working on the analysis of this data. And we were sort of competing, but the good thing is that we published and they haven't published. And we think that they were using the old model from BOS and EBOS, and now they are trying to. And we were scared for a few months because it was public. Everybody could.
There's no more questions. Thanks once again.